Howdy, welcome to another video, section 3.4, Invalid Conclusions. This is based on the textbook First Course in Mathematical Logic by Patrick Suppes and Shirley Hill. Determining invalidity. Now remember that if the premises are true and the argument is valid, then the conclusion that follows will be true. It's guaranteed to be true. All men are mortal, Socrates is a man, therefore Socrates is mortal. The premises are true, the argument is valid, so the conclusion must be true. And we can write this general principle in symbolic notation. So if we have true premises, and we have a valid argument, then the conclusion will be true. Thus, if the conclusion is in fact false, then either the premises were false or, conclusively, the argument was invalid. So we have our first premise here. T and V implies C. Second premise, not C, therefore not parentheses T and V. But by De Morgan's law, that's equivalent to not T or not V. So this right here, not T or not V, is equivalent to this. The premises were false or the argument was invalid. So given this, how do we know when an argument is invalid? Answer: the conclusion to an argument must be false, even though the premises were true. So that is to say that if we have not T or not V, we know for a fact that this is not the case. So we have true premises. It therefore follows that it must be the case that the argument is not valid. That is to say, it is invalid. And this is going to be the key to this lesson. Let's look at an example from page 122. If you are a son, then he is your parent. He is your parent, therefore you are his son. Well, right away that seems a very fishy argument, and if you remember mixed hypothetical syllogisms, it is in fact invalid because it's committing the fallacy of affirming the consequent. So the conclusion is invalid. Let's think a little bit more about this. To see that the argument is in fact invalid, we can find an interpretation of the argument where the premises are true, but the conclusion is false. Now this dovetails very nicely with the last slide. So if we know for a fact that we have true premises, and if we know for a fact that we have a false conclusion, then the argument must be invalid. Step 1, we're to symbolize the form of the argument. So, for example, we have if P then Q, Q therefore P. In step 2, we're going to make up an example with true premises but a false conclusion. And the textbook gives this example from page 123. If you are a citizen of Maine, then you are a citizen of the United States. And that in fact is a true premise. The second premise is you are a citizen of the United States. That's a true premise, at least for me. Therefore, you are a citizen of Maine. Well, that in fact is false. I'm not a citizen of Maine. So we know the premises are true, but the conclusion is false. So this argument is definitely invalid. And thus the argument from page 122, this one up here, is also invalid. It has different material content, so to speak, but it has the same structure, the same form, namely this right here. So this method can be used to show that an argument is invalid. And that's what we're going to be doing in the next few problems. Let's think more about the method of truth assignment. Recall, insofar as we start out with true premises, but we end up at a false conclusion, it necessarily follows that the argument is invalid. After all, if you have true premises, and from those true premises you get something bad from that, somewhere along the line the argument went bad. It's an invalid argument. So once again, let's consider the fallacy of affirming the consequent. Someone argues, if P, then Q, Q, therefore P. What we're going to do is assign truth values, to the atomic sentences such to determine if an argument is invalid. So we're going to create a table. So some atomic sentences may be true, some may be false. We know we want the conclusion to be false. We want to show we have a situation with a false conclusion and true premises. So the conclusion is P. So we want that to be false, so we'll assign P the truth value of false. So here we get something false. So we have a conclusion that's false. We also have these premises, if P, then Q, and Q. So we know P is false. We assigned it that value. And we could assign Q as true. So Q is true. It has a truth value of being true. We have a false antecedent, but a true consequent. We have a true conditional. So the first premise here is true. And Q we've assigned as being true. So the second premise is also true. So we have a true premise, another true premise, but a false conclusion. So therefore, the argument must be invalid. Likewise, we can do the same kind of thing with the fallacy of denying the antecedent. So someone argues, if P, then Q, not P, therefore not Q. So we want to have a table to assign these truth values. The conclusion is not Q. We want the conclusion to be false, so Q must be true, because if Q is true, but we're denying it, we get something that's false. We have the negation, so we have a false conclusion. We have the premise, if P, then Q, and the premise not P. Well, let's think about the second premise, not P. We want that premise to be true, so we'll say that P is in fact false. So if P is false, then we negate it, so we get something that's true. So the second premise is true. P is false. Q is true. So we have a true conditional. So this premise is also true. So we have the two premises, both are true, but the conclusion is false, so therefore the argument is invalid. The fallacy of denying the antecedent is indeed a fallacy. Let's look at the example from page 125. We're given two premises and a conclusion, and our goal is just to show the conclusion is invalid, that we have an invalid argument. Here I cheated a little bit. I won't in the next slides, but I've already assigned the truth values for each of the atomic sentences. So we're going to say that these atomic sentences are true and that this one is false. So we have the conclusion, not P or not Q. We have the premise P and not R. And the very long premise parentheses, P and Q, close parentheses, implicates, parentheses, P implicates Q, close parentheses, or S. So let's look at the conclusion and determine the truth value of that molecular sentence. P is true, but we're negating that, so then that is false. Not P is not the case. Q is true, but we're negating this, so that's false. And in this disjunction, both options are false, so it must be a false disjunction. So we have a false conclusion. Let's look at the second premise. P is true, R is false, but that's being negated, so it's true. And we have this conjunction, and both of the choices are true, so it is a true conjunction. So we have a true premise. And in our first premise, let's look at this little conjunction here. P is true, Q is true, so that is a true conjunction. If we look at this little conditional, P is true, Q is true, so this conditional is true. And then we have this disjunction here. S happens to be true. Both options are true in the disjunction, so that disjunction is true. And now we have this overall conditional. The antecedent is true, the consequent is true, so it's a true conditional. So it's a true molecular sentence, so we have a true premise. So we have a true premise, false conclusion. The argument is invalid. It's a little tedious to be sure, but it's not that difficult, and it definitely works, and it's a good way to show that an argument is invalid. Together, let's look at exercise 7b, or at least part of exercise 7b, from pages 126 to 127. If any of the symbolized arguments below are valid, show a derivation of the conclusions by means of a complete formal proof. If they are invalid, prove it by a truth assignment. Number 3, we're asked to prove not Q. Really, it's asking us, does not Q validly follow from the 3 given premises? Now, before we write anything down on our piece of paper on the computer screen, let's just think about this in our heads a little bit. What are our 3 premises? We have if T, then Q, not T or Q, not R. Where our third premise does categorically say something the case, namely that R is not the case. But R doesn't show up in premise 1 or 2, so how in the world is premise 3 going to help us? It's not going to, right? In premise 2, we just have a disjunction, but nothing's being affirmed or denied. And likewise, in premise 1, nothing's being affirmed or denied because we just have a conditional. We have an if-then statement. So how can we get not Q? Definitely, we're not going to be able to. So this is an invalid argument. But we want to prove that by a truth assignment. So we're going to assign some atomic sentences, perhaps, as having the value of being true, and some, perhaps, as having the value of being false. And we're going to assign each atomic sentence these truth values in such a way that the conclusion is false and all the premises are true. So we have the conclusion of not Q. We have the premise not R. We have the premise not T or Q. Okay. And we have the premise if T, then Q. So let's think about the conclusion first. The conclusion we want to be false. So what do we assign Q to make it so? Q is just an atomic sentence, but it's a part of an overall molecular sentence. Just a part of a molecular sentence. Well, Q we better say is true, right? So if Q is true, then that molecular sentence will be false because we have the negation. So we have a false conclusion. And that's exactly what we want. We want a false conclusion. So Q must be true. And of course, when we're doing this, we have to be consistent. So if we say Q is true, we better make sure each time Q shows up, we say it's true. And likewise for the other atomic sentences. Now what I'd like to do now is to look for the premises where Q appears. So for example, it appears in the second premise. So we have a disjunction, and Q happens to be true. Now in this case, it's a disjunction, so it really doesn't matter. Given that Q is true, it doesn't matter what the other disjunct is. It could be true or false. The disjunction as a whole will still maintain its its value being true. But for the heck of it, let's say that t is false, but that's being negated, so it's true. So we have the choice true or true, which of course is true. So we have a true premise, and that is exactly what we want. So true, t, we're saying is false. Let's look at the first premise. We have if t then q. T is false, but q is true. And that conditional, therefore, is true. So we have a true premise. And again, that's exactly what we want. And finally, the premise not R. We want that premise to be true, so R better be false. So we'll say R is false. R is false, but that's being negated. So now we have a true molecular sentence, we have a true premise. And we've proved that it's definitely an invalid argument. So we have each premise is true, but the conclusion is false. Now let's look at number 4. We're asked to prove S given 4 premises. Again, let's think about this in our heads a little bit. All right, so we have R or S, not P, Q or not R, P if and only if Q. So we have not P, that's being definitely asserted. That we can definitely relate with the fourth premise. So we can say Q is not the case. But if Q is not the case, then not R is the case. Because R is not the case, S is the case. Well, we did prove S, okay, in our head, right? In our head. So this is a valid argument. We better demonstrate that step by step. So for our fifth sentence, we can get if Q then P, because we have a biconditional law from sentence 4. So for our sixth sentence, so we have 2, we have not P, so we can get not Q there because of modus tollens with sentences 2 and 5. So we're denying the consequence, so we can thereby deny the antecedent. But if Q is not the case, then we can affirm not R. So for our seventh sentence, we get not R because we have a disjunctive syllogism with sentences 3 and 6. If R is not the case, then S must be the case, right? So we have S, so we have a disjunctive syllogism with sentences 1 and 7. We have just proved that S is the case. It is a valid argument. Let's just do 2 more problems for exercise 7b, number 5 and number 6. Number 5, we're asked to prove T, but can we even prove T given those 3 premises? Nothing's being categorically affirmed or denied. We don't have any kind of pure hypothetical syllogism going on. So right from the outset, this looks invalid. But we need to prove that with the truth assignment. We have the conclusion T, the premise if T, then R, the premise P or R, and the premise not parentheses P or Q. I think we should start at the conclusion. We want the conclusion to be false, so the only way that can happen is if we assign T the value of being false. So we have a false conclusion. Does T show up anywhere else? It does in the third premise. Now, to make that premise true, R can either be true or false. So either one will do, but the question is, what about the other 2 premises? So we had to think ahead a little bit. And if we make a mistake, that's all right too. We'll just backtrack and just correct ourselves. So what I think we should do actually is look at the first premise. We have a negation overall, but within the negation is a disjunction. So what would P and Q have to be such that that premise will be true? Well, it would have to be false. We would have to have P is false, Q is false. So we have a disjunction that's false. But that's being negated, so then you get something true as a premise. So P and Q must be false. But again, what about R? Well, in the second premise, we have P or R, and P is false, so R better be true in order for that premise to be true. So we can work on the third premise. So T is false, R is true. The conditional is thereby true, so we have a true premise. We have three premises. Each of them is true, but a false conclusion, so this is an invalid argument. So let's look at number 6. We're to prove not R, and we have 4 premises. So here we have nothing categorically affirmed or denied. We have disjunctions and conditionals. Doesn't look like there's a hypothetical syllogism, so it looks invalid. So we better prove that with the truth assignment. We have the conclusion, not R. The premise, P or not Q. The premise, S or R. The conditional, if Q then S, as a premise. And the first premise is if P then T. So let's start with the conclusion, which is not R. We want it to be false, so R has to be assigned the value of being true. Actually, I don't want that color there. That's all right. That's all right. Well, at any rate. So let's look at what else we have here. So R shows up in the third premise, and R is true. So S can be true or false in this disjunction. Let's see, and S shows up in the second premise. So yeah, we can say S is true. So in our third premise, we have a true molecular sentence. What about Q? Well, Q shows up in the fourth premise, right? P or not Q. I think we could assign that still. I think we could still do our true streak, so to speak. Why not? So then we still will get a true premise. If we look at the fourth premise, so we're saying Q is true, but it's been negated, so we have false. So P will have to be true. We get a true premise. And if we look at our first premise, we know that P is true, T is true, so that's a true premise. And so we have thereby proved that this argument is definitely invalid. There is wiggle room here, by the way, I should point out. So in this case, I was able to assign each atomic sentence as having the truth value of being true, but there was a little wiggle room. Let's kind of think about this. What I could have done, I could have assigned P and Q as false, because look here, right here in this fourth premise. So if P is false and Q is false, that still would be a true premise, because that Q is being negated. And likewise here, you have a conditional. If the antecedent and the consequent are both false, the conditional as a whole is still true. So that's okay if you end up with a different selection than I do or the textbook does in these kinds of cases. All that matters is that you're consistent. So if I say that P is true, I better make sure it's true in each application. At any rate, not too bad. Let's move on. Before we call this video quits, let's look at part of exercise 7a. It's kind of nice to move away from all the symbols and think about concrete examples. After all, shouldn't the symbols actually represent something? So here's an argument. If Mary leaves early, then she walks home with Sally. Either she walks home with Sally or she meets Karen. Mary leaves early, therefore she does not meet Karen. Is this argument valid or invalid? Well, we're told that Mary does leave early, so it is the case that she walks home with Sally. So everything really hinges on the second premise here. Either she walks home with Sally or she meets Karen. But by default, the or is inclusive. So just because she's walking home with Sally does not the case that she meets Karen. So you could have both being the case. So that's really where the fallacy is. So without doing a truth assignment, we can see this argument is invalid. But wait a minute. In real life, we often treat the or as exclusive, not inclusive, right? So is every argument of this structure fallacious? Actually, I would say no, because oftentimes we do use the or in an exclusive manner. In fact, in older logic, they would make a distinction between what's called modus poendo, tollens, versus modus tollendo, ponens. So here you would have something like S is either P or Q, S is P, thus S is not Q. So here, with modus poendo tollens, we're dealing with an or that's exclusive. In everyday life, again, we use or in an exclusive way. So there's a little bit of subtlety here, I suppose. Whereas modus tollendo ponens is really the same thing as what we can call the disjunctive syllogism. And here, the or is inclusive. Or it actually could be exclusive, by the way. It could be exclusive, and this would also still work, because you're denying one of the disjuncts, so the other one must be true. But at any rate, should we do a truth assignment? I don't know. I don't want to, so let's just move on. All right, just one more argument for this video. Either the water is cold or the day is not hot. The day is hot, but if the pool has just been filled, then the water is cold. Therefore, the pool has just been filled. Is this valid or invalid? We do know that the day is hot, and that contradicts in our disjunction the day is not hot. So it is the case that the water is cold. We know that. So the argument really hinges on this third premise here. If the pool has just been filled, then the water is cold. We know the water is cold, but could we then say the pool had just been filled? So we really have the fallacy of affirming the consequent. So that's really at the heart of what makes this argument invalid. Okay, just by thinking about it. But let's actually do a truth assignment here to also show that this is indeed an invalid argument. So we'll first write this in symbolic notation. We have, let's see, we have C or not H. That's our first premise. Our second premise would be just H. The day is hot. 3, we have a conditional. Let's say if P, then C. And then we're concluding that P is the case. But this is an invalid argument. So let's do a truth assignment. So we have true, we have false. We have the conclusion. Just pick another color, why not? All right, so we have the conclusion P. We have the premise if P then C. We have the premise H. And the premise C or not H. We'll of course say that P is false. So then we get a false conclusion with that truth assignment. We'll want to say that C is true, so then we can have our third premise as P being false, C being true, so then we can have a true premise. So we'll want, for our second premise, we want H to be true, so that we have a true premise here. So C is true, H is true, but that's negated, so we have false. We have a disjunction, one disjunct is true, so we have a true premise. So we have all true premises but a false conclusion, so the argument must in fact be invalid. So by truth assignment, we see why it's invalid. So this is one way to show it, but in my mind at least, while this exercise in truth assignment is interesting, really the fundamental reason that this argument right here is incorrect from number 2, this is wrong because we really are engaging in the fallacy of affirming the consequent. All right, ladies and gentlemen, up next is section 3.5. I'll see you soon. Thanks so much for watching.